Topics in post-harvest technology. Pre-cooling methods, vacuum and hydrovac cooling, Part 1. Some background. Pre-cooling is the rapid removal of the heat from a commodity before it is placed in storage or before it is shipped. Pre-cooling helps to maximize shelf life by rapidly reducing a product's respiration rate and its rate of water loss. Pre-cooling reduces the refrigeration requirements in storage and during the transportation of produce. So let's discuss vacuum cooling. It is a pre-cooling method which utilizes low air pressure to cause water to boil at a low temperature, which then cools the product. In the United States, a BTU, or British thermal unit, is defined as the amount of heat it takes to raise 1 pound of water 1 degree Fahrenheit. Or alternately, you can think of it as the heat that is emitted when 1 pound of water cools 1 degree Fahrenheit. However, when a liquid boils, it undergoes a phase change. A phase change represents a change to a different state of matter, in this case, from a liquid to gas. Boiling a liquid requires much more energy than is needed to simply raise the temperature of the liquid, as the resulting gas is in a much more energetic state of matter. When 1 pound of water is boiled at sea level, rather than taking 1 BTU, it takes 970 BTUs to convert the pound of liquid water to a pound of water vapor. The value 970 BTUs is referred to as the heat of vaporization for water at sea level. By changing the pressure on the surface of a liquid, the boiling point can be manipulated. At lower pressure, the boiling point is lower. At higher pressure, the boiling point is higher. The pressure of air at sea level has been defined as 1 atmosphere, which is equal to 14.7 pounds per square inch, or 760 millimeters of mercury. At 1 atmosphere, again, water boils at 212 degrees Fahrenheit or 100 degrees centigrade. And note, during the boiling process, the liquid water stays at 212 degrees Fahrenheit. However, in a food pressure cooker with an internal pressure of 29.7 pounds per square inch, water will boil at 249.8 degrees Fahrenheit. Therefore, our food will cook much more quickly since the water is actually much hotter. In contrast, at Lake Tahoe, with an elevation of 6,224 feet, and thus where the air is much thinner, meaning less air pressure, water will boil at approximately 200 degrees Fahrenheit. This means that our food will take longer to cook than at sea level. This is a graph that represents changes in the boiling point of water as affected by air pressure. When you look at the graph, notice on the x-axis at the right, we have 760 millimeters of mercury, which is actually 1 atmosphere, and that's the average pressure of air at sea level around the world. Notice that at 760 millimeters of mercury, water boils at 212 degrees Fahrenheit. Now, if we begin to reduce the air pressure to less than 760 millimeters of mercury, you will notice that the boiling point decreases, and as we get close to zero pressure, the boiling point of water very quickly decreases. At 4.6 millimeters of mercury, water will boil at 32 degrees Fahrenheit. This can seem confusing, but remember, boiling is simply the rapid conversion of a liquid to a gas and can occur at any temperature. For example, at 1 atmosphere, liquid nitrogen boils at minus 320.4 degrees Fahrenheit, and no one would consider that to be hot. So do not confuse boiling with heat. Yes, boiling takes heat energy, but the liquid itself may or may not be hot, as boiling can occur at any temperature, even quite cold temperatures. Let's now discuss vacuum cooler development and operation. Vacuum cooling was developed in the 1940s at the University of California, Davis as a quick method to cool iceberg-type lettuce heads. A method was needed that did not involve water, as iceberg lettuce heads readily trap water, which makes them prone to rotting. A heavy steel rail car was converted into a cooling chamber to which was attached a vacuum pump. When the rail car was loaded with lettuce and sealed, the vacuum pump was turned on and the air pressure was reduced. As the air was pumped out, air pressure decreased, as did the boiling point of water. When the boiling point of water was the same as the temperature of the lettuce, the water in the tissues immediately began to boil. This point, the point at which the water begins to boil in the lettuce tissues, is known as the flash point. The pump quickly reduced the air pressure to 4.6 millimeters of mercury, which is a strong vacuum. At 4.6 millimeters of mercury, water will boil at 32 degrees Fahrenheit. Since at 4.6 millimeters of mercury, the lettuce in the vacuum tube was warmer than water's boiling point of 32 degrees Fahrenheit, the water in the lettuce heads continued to boil away. As the lettuce heads released water vapor, 970 BTUs of heat energy was removed from the heads for each pound of water vapor that formed. Since the heads now contained less heat energy, they were colder. The lettuce effectively cooled itself. And here's a photograph that shows a load of vegetables that's being cooled in this rather large vacuum tube. The product is palletized and placed on a conveyor. When the conveyor is turned on, the pallets will move into the vacuum tube and the raised steel doors will then drop down. The doors have gaskets so that when the vacuum pump is turned on, the gaskets will hermetically seal the chamber. Hermetic means airtight. Hermetic seals will allow the vacuum pump to reduce the air pressure in the tube much more quickly and efficiently. This shows the vacuum tube in operation, and you really can't see anything, but inside there's a very strong vacuum that has been formed. Water vapor is being released from the product, and the product is being cooled through the release of that water vapor. Vacuum cooling works best with produce that has a high surface to mass ratio, such as iceberg-type lettuce. High surface to mass means that there is much more surface area when compared to the weight of the product. A low surface to mass commodity would be something like an Irish potato, which is relatively dense and has a fair amount of weight for a relatively small surface area. Iceberg lettuce is cooled efficiently in a vacuum tube, but an Irish potato is very slow to cool in a vacuum tube because it is limited in its ability to quickly lose water from its tissues. During vacuum cooling, for every 1% water loss from the iceberg lettuce, it cools approximately 11 degrees Fahrenheit. So if the lettuce were picked at 65 degrees Fahrenheit, and we wanted to cool it to 35 degrees Fahrenheit, the heads would lose less than 3% water. Since the vacuum occurs within the heads, not just outside the heads, water loss occurs from all surfaces, inside and out, making the water loss more uniform. Therefore, wilting of iceberg-type lettuce is not usually a problem with vacuum cooling. Vacuum cooling of iceberg lettuce is quick and does not damage the heads. Since boiling is just the rapid conversion of water to its gaseous form, the tissues are not cooking, nor are they being damaged by the boiling process. Vacuum cooling of iceberg lettuce was so successful a pre-cooling method that it became the standard way to cool iceberg-type lettuce, and we're still using it with iceberg-type lettuce to this day. So what are the advantages and disadvantages of vacuum cooling? With respect to advantages, it is a gentle method and is relatively quick. No water is added to the product, so wax cartons are not necessary with this pre-cooling method. It can also be used with a number of commodities. Disadvantages are that wilting can be a problem if you have a low surface area to mass commodity, such as leaf lettuce. Iceberg lettuce has a much higher surface area for its weight than does leaf lettuce. It is expensive to buy or rent vacuum coolers, and it's expensive to operate them since it takes a lot of electricity to run the vacuum pumps. Worker safety is also a concern. If a worker were to be inside the tube when the doors go down and the air were pumped out, as you can imagine, the worker would die of asphyxiation. At below approximately 10% oxygen, they would pass out and die. Therefore, in many of these tubes, there is a stop button inside so that should a worker be inside and the doors close, he or she can run and hit that button, which turns off the vacuum pump and which causes the doors to raise. So what are the summary points? Pre-cooling is the rapid removal of product heat before storage or transport. Vacuum cooling is a type of pre-cooling in which air pressure is reduced to cause a commodity's tissue, water, to boil at 32 degrees Fahrenheit. For every pound of water lost as vapor from the tissues, 970 BTUs of heat energy is removed, so the tissues become colder. For every 1% water loss from the tissues, there is an approximate 11 degree Fahrenheit drop in tissue temperature. Since the vacuum occurs within as well as without the tissues, water loss is fairly uniform, though wilting can still be a problem for lower surface area mass produce such as leaf lettuce. Vacuum cooling works best with produce that has a high surface to mass ratio, such as iceberg type lettuce.